In the previous lecture, I explained how to deal with unbiased series clippers. Now we will solve problems based on biased series clippers. In the first problem, we need to determine VO, the output voltage for the input shown. This is the input waveform and we have to plot the output waveform. I am calling this circuit biased series clipper circuit because we have additional DC source present in this circuit. And whenever you have this situation when there is additional DC source present in the circuit, always try to find out effect of this DC source on the state of the diode. By state of the diode, I mean whether the diode is forward biased by this DC source or it is reverse biased by this DC source. And for this purpose I will forget VI, the input voltage source, and I will only consider one source in this circuit, that is the DC source. The current will have this direction because of this DC source entering to the negative terminal and starting from the positive terminal. This direction of current is matching with the direction of arrow in the diode symbol. So this 5-volt supply is forward biasing the PN junction diode we have in this circuit. Now we will try to plot the output waveform for the first half cycle from 0 to T/2. The input voltage VI is equal to 10 volts throughout this half cycle. You can see this will be the polarity plus minus, and we have current in clockwise direction because of VI, like this. This will be the direction of the current because of VI, and the direction is matching with the direction of arrow. So VI is also forward biasing the silicon diode. Both the sources are forward biasing the silicon diode, so I will replace it with its equivalent model like this, plus minus 0.7 volts. And now we can easily calculate the output voltage by using the Kirchhoff's voltage law. VO is equal to VI minus 0.7 volts plus 5 volts. This is what we have from the Kirchhoff's voltage law. VI is equal to 10 volts. So simply we have 10 minus 0.7 volts plus 5 volts. When you solve this, you will have 14.3 volts as the value of output voltage. I will quickly plot it. 14.3 volts as the value of output voltage for the first half cycle from 0 to T/2. Now we will find out the output voltage for the next half cycle from T/2 to T, and we have minus plus as the polarity. Because of this, the silicon diode will be reverse biased because direction of current is anti-clockwise, which is opposite to the direction of arrow, and 10 volt is the value of VI. 10 volt is the value of VI, which is greater than 5 volt. So this 5 volt is not sufficient enough to forward bias this diode alone. This is reverse biasing the diode. So finally the diode is reverse biased, and I will replace it with open circuit. When circuit is open, there will be no current through the load resistance, so output voltage is simply equal to 0 volts. So for the next half cycle, the output voltage is equal to 0, and again it will be 14.3. It will be 14.3 for the next half cycle. So this is how the output waveform will look for the problem number 1, and you can see this circuit is negative clipper because we are clipping the negative portion of the waveform. Now we will solve the second problem. In this problem also we have to plot the output waveform VO for the input shown. We are having the sinusoidal input with Vm equal to 20 volts. You can see the maximum voltage is equal to 20 volts. In this problem, the DC voltage source is having 3 volt as the magnitude, and this voltage source is forward biasing the diode, and the diode is ideal. When you only consider the 3 volt supply, you will find the direction of current is like this from right to left, and it is matching with the direction of arrow, so it is forward biasing the diode. And for the first half cycle from 0 to T/2, plus minus is the polarity of the input voltage VI, and if you only consider VI and neglect the additional DC voltage source, you will find it is reverse biasing the ideal diode. This is reverse biasing the ideal diode. So when Vi is smaller than 3 volts, the diode will be forward biased, and when Vi is greater than 3 volts, the diode will be reverse biased. I will write this down. The diode will be forward biased when the input voltage is less than 3 volts, and the diode will be reverse biased when input voltage is greater than 3 volts. When diode is forward biased, I will replace it with short circuit because it is ideal diode, and the output voltage VO is equal to Vi minus 3 volts. And when Vi is greater than 3 volts, the diode is reverse biased, and I will replace it with the open circuit. So the output voltage is simply equal to 0 volts. Now I will plot the output voltage for the first half cycle. When Vi is less than 3 volts, this means for this and for this section of the input waveform, VO is equal to Vi minus 3 volts. So when Vi is equal to 0, VO is equal to minus 3 volts. When Vi is equal to 3 volts, VO is equal to 0 volts. So the waveform will look something like this. This is minus 3 volts. This is 0 volts. Vi is equal to 3 volts here. So we have 0 volts here. Vi is equal to 0 volts here. So we have minus 3 here. So this is how the waveform will look for this interval of time. After this, when Vi is greater than 3 volts, this means for this section of the input waveform, the output voltage is equal to 0 volts. So the output voltage will remain 0 during this time interval. Now I will plot the output waveform for the next half cycle from T by 2 to T. Minus plus is the polarity of the input voltage Vi, and you will see the direction of current is anti-clockwise. So the direction of current is matching with the direction of arrow in the diode symbol. So Vi is forward biasing the diode, and this 3 volt DC supply is also forward biasing the diode. So diode will be forward biased for this half cycle, and I will replace it with the short circuit. I will use Kirchhoff's voltage law to find out VO. VO is equal to minus Vi minus 3 volts. You can easily use the Kirchhoff's voltage law to obtain the output voltage. When Vi is equal to 0, this implies VO is equal to minus 3 volts. This is what we have. When Vi is equal to 0, VO is equal to minus 3 volts, and when minus Vi is equal to minus 20 volts, the output voltage is equal to minus 20 minus 3. This is equal to minus 23 volts. So the waveform will look something like this. The peak value is equal to minus 23 volts, and when Vi is equal to 0, VO is equal to minus 3. So here we have minus 3, and it will go like this. This portion is similar to this portion for the next positive half cycle. In the same way, the waveform will repeat itself. I think it is clear to you now. If you compare the biased series clippers and unbiased series clippers, you will find biased series clippers is little bit tough to analyze because we have additional DC voltage source present in this circuit, and this DC voltage source will alter the state of the diode. It may reverse bias the diode, or it may forward bias the diode. So you have to analyze it carefully. Follow the steps that I have explained in this lecture, and if you have any doubt, you may ask in the comment section.